All right, let's dive right in. Today, we're taking a tour of the single most important part of your computer, its brain. We're talking about the central processing unit, or the CPU. We're going to pull back the curtain and see exactly what makes this tiny little chip tick. I mean, really think about it. You click on an icon, and just like that, a whole program launches. How does that happen? What's going on in that split second? Well, it's not magic. It's actually a lightning-fast journey your command takes, and today we're going to follow it right into the heart of the machine. That entire journey, that whole process, it's built around one simple idea: processing. It's this procedure that takes raw, kind of meaningless data and turns it into useful information. And you know who the star of that show is? The CPU. It's the one doing all the heavy lifting. So, what is a CPU, really? Well, it's the electronic circuitry, usually sitting right on the motherboard, that executes instructions. And that brain analogy? It is absolutely perfect, because just like our brains, it's the thing doing all the thinking, controlling and coordinating literally every single thing that happens in the system. Its main job really boils down to this simple three-step loop that just repeats over and over billions of times a second. First, it accepts data and instructions. That's your click. Second, it gets to work and processes that data. And third, it either stores the results somewhere or sends it to your screen. Input, process, output. That's the heartbeat of your computer, right there.
But here's the thing. The CPU doesn't do all this work alone. It's more like a super efficient two-person team working together in a tiny little control room. So let's meet the key players who actually make all this magic happen.
On one side, you have the control unit. Think of this as the director or maybe the traffic cop. It doesn't do the math itself, but it reads all the instructions and tells everybody else what to do and when to do it. Then, you've got the arithmetic logic unit, or ALU. This is the powerhouse. This is the math whiz that does all the calculations and makes all the logical decisions. So one directs the traffic and the other does the actual work. Now, to work this insanely fast, the CPU needs a way to keep track of what it's doing right this second. And for that, it has its own special, super high-speed memory called registers. You can just think of them as tiny little digital sticky notes holding the exact piece of data the ALU needs for its very next calculation. So we've got our director, we've got our calculator, and we've got our sticky notes. But how do they all talk to each other? And how do they talk to the rest of the computer, like your main memory? Well, they communicate using a system of electronic pathways called buses. So, welcome to the digital highway system.
And just like in a real city, it's not just one giant road for everything. That would be chaos, right? Instead, it's made up of three very distinct types of highways, and each one has a very, very specific job to do.
This table breaks it down perfectly. You've got the address bus. It's a one-way street. The CPU uses it to shout out a memory location, kind of like putting a destination into your GPS. Then there's the data bus. This is a two-way street where the actual data, the passengers, travel back and forth. And finally, the control bus carries all the commands and timing signals, basically the traffic lights and road signs that keep everything moving in perfect sync. So you might be thinking all CPUs are pretty much built the same way, right? Well, not exactly. Over the years, two major design philosophies have popped up for how to build the CPU's fundamental language, its instruction set. And this brings us to CISC versus RISC. CISC stands for Complex Instruction Set Computer. Think of it like a Swiss Army knife. It has hundreds of complex instructions where just one command can kick off a whole bunch of steps. Then you have RISC, which is Reduced Instruction Set Computer. This is more like having a small set of specialized single-purpose tools. There are fewer, simpler instructions, but each one executes incredibly fast. Okay, so this brings us to the big question, the one everybody always asks. What actually makes a computer fast? We've seen all the parts, but how do they all come together to give you the performance you actually feel? And here is the single most important takeaway. It is never just one thing. I know marketing loves to focus on one big number, like clock speed. But real performance? It's a team effort. It's this delicate balance between a bunch of different factors all working together. To really get this, let's go back to our highway analogy. Early computers, they used an 8-bit data bus. This was like a narrow, single-lane country road. Sure, it worked, but you could only move a tiny bit of data at a time. It created this massive traffic jam. Now, let's jump forward to today. Modern computers use a 64-bit data bus. This isn't just a road anymore. This is an 8-lane superhighway. It can move 8 times more data in the exact same amount of time. And that, as you can imagine, dramatically boosts the computer's overall speed. And you can actually see this evolution of the highway over time. We went from the 16-bit ISA bus in old PCs to 32-bit buses, then to the 64-bit PCI bus that became a huge standard, and now, of course, we have things like USB that connect pretty much everything. It's just this constant story of getting wider, faster, and more versatile.
So let's bring it all home then. What makes a computer fast? It's the whole team. It's the clock speed, which is how many operations it can do per second. It's the amount of RAM, that's the computer's active workspace. It's the bus width, or how many lanes are on our data highway. It's the cache memory, that super fast buffer. And finally, it's that processor design we talked about, the whole RISC versus CISC idea. They all have to work together.
From your mouse, down the digital highway of the buses, right into the CPU, where the control unit directs the ALU to do its thing using those little sticky note registers, all before sending a result back out to your screen. It's this incredible, high-speed dance of logic happening billions of times every single second. And now you know exactly how it all works.